In this work, we present a multi-frame super-resolution algorithm that supplants demosaicing in mobile phone burst photography pipelines. Our algorithm produces images with higher resolution and improves signal-to-noise ratio. It also avoids visual artifacts that are characteristic of demosaicing techniques, such as chromatic aliasing, maze, false gradients, and moire patterns. Here, we present the steps of how our algorithm merges information from multiple frames. The first step of our algorithm is frame acquisition. We do not require any special capturing conditions as our method is designed to work with natural hand motion. We observe that hand tremor is strong enough to provide displacements of at least multiple pixels within the frame burst. When aligned to a common reference frame, this translates to random subpixel offsets and together with signal aliasing provides sufficient information to reconstruct the higher resolution signal. For each captured frame, we analyze the local image gradients, localizing edges, corners, and textured areas. This allows us to decide how much resolution enhancement or spatio-temporal denoising we wish to obtain. Based on gradient information, we adjust local frame contribution weights. We use anisotropic Gaussian radial basis function kernels, stretching them along object edges and flattening them in areas where we detect signal variation within expected noise levels. As described so far, the method would produce strong artifacts in the case of complex non-aligned movement, alignment errors, or occlusions. Here, we observe that after local alignment, the sequence contains many alignment errors. Without intervention, those areas would contribute to fusion artifacts. To avoid them, we define a local motion robustness model that creates a per-frame robustness mask. Using this, we detect misaligned areas and remove their contribution to the final image. This allows us to merge such sequences without fusion artifacts. Now, we show the results of our algorithm compared to other techniques. In the first comparison, we generated synthetic image bursts from the Kodak and McMaster datasets and compared our algorithm against different demosaicing techniques. Since our algorithm is able to use additional information from multiple frames, we obtain a more accurate reconstruction and avoid demosaicing artifacts. We also compare our algorithm against demosaicing techniques using raw bursts captured with a mobile phone. We ran the demosaicing techniques on both a single frame as well as the output of the burst merging technique from Hasanoff et al. Our technique shows more image detail and the least amount of structured artifacts or zippers. Here, we show visual results of our algorithm when used inside the end-to-end burst processing pipeline by Hasanoff et al. Our algorithm can merge a varying number of frames. In the case of good lighting, 7 frames is usually enough to provide sufficient subpixel coverage and additional information to reconstruct a high-quality picture. In the case of low light and low signal-to-noise ratio, we observe a temporal denoising effect, which significantly improves the image quality as the number of merged frames increases. For more details, we refer you to our paper.